we have the practical approach to automate the discovery and eradication of open source software vulnerabilities at scale by Aladdin Almubayed. I have a couple of announcements real quick. The Blackhat Arsenal is located in the Business Hall in Mandalay Bay, Oceanside, and Shoreline ballrooms. Lunch is going to be in Bayside AB from 1 to 2:30. And if you would take a moment to please silence your cell phones, it would be absolutely appreciated. And with that, if you'll give us a round of applause, we'll get you Aladdin and get started.
Good luck. Thank you. Thanks very much. Raise your hand if you realize this talk is going to be about open source security. Almost everyone. Good, good. So you read the title of my talk before you decided to come in here. Great. But you might be asking yourself a question, why another talk in open source security? Well, when I went and looked at all the presentations from various conferences in open source security, none of them actually gave solid practical approach on how to do this. So today, I'm going to give you a practical approach so you can automate both the discovery and remediation of open source vulnerabilities. This way, I can inspire more people to talk about open source security, and we can collectively improve the state of open source security. Now, you know, when we talk about open source security and the problems with it, the analogy that I like to use is a big party of people. So here we are in Vegas, the center of parties. Imagine that you have a big party and you invited all of your friends. They invited all of their friends, which they know very well. And now you have so many people in the party that you wouldn't know. So you're entirely depending on your friends to make good decisions, to bring in friends that they know very well. But you will never know. There could be people walking in. There could be people, walking in they never invited. Well, this is the analogy of the problem we face with open source security or open source dependencies. So what we're going to talk about today, we're going to first introduce the problem of open source security. We're going to put our hacker hat and talk about some attacks in open source dependencies. We're going to share our approach on how did we actually solve the problem. And then we're going to talk about some future work. By end of this talk, my goal for you is to have enough information so when you get back to your team, you can avoid the potential problem that open source introduces. This way, you can actually save a bunch of time and energy on figuring out how to avoid it. Before I jump in, let me first introduce myself. My name is Aladdin, and I am on the application security team at Netflix. Our team's charter is to help engineering teams at Netflix improve the security of their software. I think everyone in this room agrees on the actual value of open source. This adoption has been accelerating over the last 10 years or so. And to think about it, this is a really good trend for the industry. It makes us move faster, we can develop more tools, and also gives us more flexibility and agility. But we all share the same frustration when it comes to finding and fixing open source security vulnerabilities in our ecosystem. Let me tell you this. This is what your day or week would look like. So you come into the office on Monday morning, you're very excited, and you have your cup of coffee, and you started reading the news when you suddenly saw this. A serious remote code execution vulnerability was found in one of the popular open source Java packages. Well, what happens to you? You're freaking out. And now you must get into it. So you started working on it, but there are so many questions you need an answer for. So you start the process of finding the answer to all these questions. You come back on Tuesday morning, you continue working on it, and you're missing lunch. And now your whole week is gone. According to a report from Sneak, the number of these vulnerabilities in open source is constantly growing, and there is no sign of it slowing down. So guess what? the thing that you had to do on Monday, you probably have to do 6 of these every week. Do you want to do that? I do want to do that. You don't want to do that. Imagine how much time and resources you and your developers have to spend to deal with this problem. So that's the actual real motivation for us to develop a practical approach. I really don't want to waste my week doing this. I need a solution that will let me respond faster with less effort from fewer people, also more precisely, and with more stability and predictability. Now let's ask the question, why is open source security hard to fix? Well, if you think about open source security, there are unique challenges. Most developers have very limited ability to evaluate the risk of third-party dependencies. Also, the sheer volume of these vulnerabilities is huge. It makes it very, very hard to prioritize. And sometimes also, developers don't have control over what we call transitive dependencies. So what is transitive dependencies? So imagine you are owner of a library called A, and that library is pulling another library called B. B in this case is called direct dependency. But B also is relying on another library called C. And C in this particular case, it's called indirect dependency. D is in this case also is called nested dependency, which B relies on both D and C relies on D. Does anyone know what's this? Any guesses? Say that again? Tree of life. I like that. It's not a jellyfish. This graph actually shows the dependencies between software packages in Python. It's a huge. This is another graph that shows the dependencies in Maven. Look at the complexity of all these dependencies. This large number of dependencies create multiple problems for developers. One major problem it creates is called dependency hell or dependency conflicts. Now, so far we have been talking about vulnerabilities, non-malicious mistakes that creates risks in code. However, there is also code that is actually malicious, code that does not require an additional attacker. The attacker comes with the library. The attacker actually is in the library. How does that actually happen? This is what we call the supply chain attacks. And typically, the attackers prefer to use covert channels to infiltrate data from organizations. And so what they do is they go and they try different covert channel attacks, such as phishing. But those results in fewer results, yields fewer results, and also will be detected earlier. One of major covert channel attack is called supply chain attacks. In this case, or in this example, they target third-party dependencies. But why is this bad? Well, first of all, they are cheap to carry out. They don't cost a lot, and it's really hard to detect. There are thousands of packages and thousands of dependencies. And also, injecting code into open source dependencies is like hiding a tree in a forest. It's like it belongs there. And it's also creates or enables malicious attackers to scale system compromise. How does that actually happen? Now, some of you might be aware of these attacks, but I'll talk about them in case you don't. So the first one is called typo squatting. And this attack relies on typo mistakes that all of us do every day. So instead of typing npm install express, the attacker or the developer, will type in npm install epscris. So if the attacker has a control over epscris, then that malicious code gets injected. Has this actually happened in the wild? Yes, it happens for both npm and Python. In the Python example, the PyPy package named Colorama with U was typo squatting the popular package Colorama without U. And what it does, it installs a VP script that on the machine that watches the system clipboards for Bitcoin addresses and replace those addresses with hard-coded one. The other method is called package masking. And the way it works is internal packages can have the same name as an external packages. So if the package in the public repository wasn't reserved by the same internal package owner, the public package can actually mask the internal one. The reason this works is because the package that has the highest semantic version will take precedence. It results in security consequences if that external package has a malicious code. How does actually this work? So you have your developer builds a new library, and this library name is company.lib.x with version 1.2. That library gets pushed to the internal repository. You have the attacker who guessed the name of that library called company.lib.x, but with a malicious code inside it. That gets published into the external package repository, which in turn goes into, after mirroring, to the internal package inside the company. The other method is called ownership transfer. It happens when a retired developer hands over the library ownership to untrusted party. And retired developer here, very extreme thing to say, but somebody who actually doesn't have a time to maintain a specific library. So if the person took the ownership is malicious, they can actually modify the library and inject malicious code. This, in turn, gives them access to the library and also all the people who actually already trusted that code. The other method is called dangling references. And dangling references is another method where attackers will go and scan all the open source packages, trying to find hard-coded URLs or S3 buckets. And they look to see if those were dangling, meaning they were pointing at some point they were pointing at a valid resource that's owned by the actual maintainer, but then no longer pointing to that resource. So what happened is the attackers will go and reserve that domain or that S3 bucket, and in turn, they get access to all the packages that using that specific domain or that S3 bucket. So if any of these methods don't work, then attackers will try to do dependency infection. And dependency infection also is another method that you can inject malicious code into open source packages. Now, there are different ways to do this, but in order for attackers to pick targets for infection, they rely on a couple of things: the popularity and reputation of the actual package, the number of direct and transitive dependencies the package has, and also how the package classes are used in the application. Does anyone see anything strange about this picture other than the 1,000 dependencies that this package is pulling? This number of maintainers. So that's where attackers may actually look at these things as like how many maintainers actually for a specific package and how many people are maintaining that specific package. And so what they do is they compromise the maintainer accounts. So they can send obfuscated commits, and those obfuscated commits, they go and they send those to the maintainer, and the maintainer will look at them, and they probably just accept the pull request, and that gets merged, and the infection happens. They also can compromise laptops of maintainers, and they compromise the CI/CD pipeline for maintainer accounts. And CI/CD is the continuous integration, continuous deployment. How many people have seen Jenkins instances without authentication on the internet? I have seen many. And the last one is called internal package version override. And some people may get confused about how this actually works, so I'm going to explain how this works. So you have your developer in your internal organization commits code and build it and push new package into the internal repository. And in this case, it's 1.5. So that package then gets deployed to production. In a completely separate pipeline, a compromised developer or a position internal attacker can do the same. So if they actually commit the code and build a library with the same name but with a higher version, and inside that version is a backdoor, then when the next time that pipeline's first one builds, it's going to basically pull the actual backdoor into the production. So how can we protect ourselves from supply chain attacks? You can use scoped registries, and those will help you to avoid the possibility of shadowing. It ensures that you always have distinct scopes for internal and external packages. You can also use package signing and dependency locking, although you probably have to keep updating your dependency locks so you can get the latest and greatest. You can also harden your CI/CD pipeline infrastructure, and you can use proxy to force internal packages to take precedence over external one. And for maintainers, you can also use 2FA to protect your accounts. So we talk about vulnerability and vulnerabilities in packages and malicious packages. All of that problem requires the same kind of response. Now let's jump to talk about the actual real solution for this problem. So the typical approach of shift left, or the sooner is the better to catch and fix vulnerabilities, might be actually a good way to do it. The shift left approach typically accomplished by putting, like, for example, IDE plugins or scanning break CI builds. The problem with shift left approach is it leaves a lot of burden on developers to think about the problem. So the developers has to think about this problem along with so many other things, and that really increases the cognitive load on developers, which we're trying to keep low. Netflix is a microservice architecture, which means large components or large software projects are broken down into components or modules, which means those modules are built in different languages. We use polyglot. Also, Netflix is a freedom and responsibility culture, which means that every team can pick their own tooling, their own language, and their own release cycle as well. It also means flexible deployments for us. And it works very well in the cloud. So given this large-scale microservice architecture, we need to come up with some core design principles that will help support our approach. The first thing is scalability. We want to build a solution that can scale at the speed we operate. We want to have automation, so we're going to automate as much as we can. We want to ensure efficiency, meaning we want to minimize the developer disruption and also lowering the remediation cost. We want to ensure that the solution is compatible, meaning we want to be cautious about security-related updates that might break people's or developers' builds. And also enablement, which means the solution should enable and guide developers to make informed security decisions. So what is the approach? So our approach is broken into 3 stages: discovery, triage, and remediation. So let's talk about discovery. So vulnerability discovery is about finding known vulnerabilities in your ecosystem. And the way you can do this is you want to find first what are these vulnerabilities and where they come from and what is the exploitability of those vulnerabilities. The way you can do this is you can hook into multiple places, such as NVD. NVD provides you with a database you can download as a JSON file or a YAML file. So you can build automated crawlers that can help you identify these CVEs and these vulnerabilities. You can also use OSS vulnerability intel feeds, and you can also use commercial OSS feeds, which does take care of all the heavy lifting. Now you can fetch this, you can build your crawler, and you can grab all the information and build your own JSON or YAML file. You can try to diff all the data, and you fill all the missing pieces. But then at the end of the day, you'll have such, a system that kind of mostly had some information about what you're looking for. So for me, this added an additional complexity over what actually our goal for this project that we want to achieve. So I decided to actually go with the third option, which is to buy a commercial OSS feed. And this is just a feed that will provide you with all the information that you need about a specific vulnerability. So the minimum things you need to have in your feed to be able to automate your solution are the following things: the vulnerability description, whether there is an exploit in the wild, and if the particular package or library is malicious, and also if the package vulnerable method is ever executed. So this metadata will help you make data-driven decisions to be able to manage and prioritize the risk. And we're going to see that in a moment. Now, the next step is you want to have a capability to be able to map known vulnerabilities with applications or instances or impacted services based on the vulnerability data that you built or you got from NVD. So you want to build some sort of API mapper. And the way the API mapper works is you want to build some dependency graph. And the dependency graph will help you drive the data that will, so you can ask the question like, for example, who's using this particular version of this package? And the depth of the dependency also. Now, most companies rely on manifest file to be able to figure out what version in the application, what's the version that the application is using, which in turn does not actually give you what you're looking for. And this is because of the problem of semantic ranges. So if you install, for example, the load dash this way, then this command will install the latest version, which is 4.x.x. And depending on the time of the installation, this may yield different versions. So how do we actually solve this problem? So at Netflix, we built a solution called Astrid, a refactory source dependency insight. And the goal for Astrid was if an engineer who built a library and is a library producer, and they want to know the impact of their library on the ecosystem, they can go and query Astrid, and Astrid will tell them who's actually using this particular version of the library. So we cannot utilize the system to be able to tell us who's using a particular version of a package. So how does it actually work? So Astrid relies on three main stages. They look at the published artifact indexing, the deployable module indexing, and indexing of AMI manifests. So published artifact indexing works this way. So imagine you're publishing an artifact jar file. That jar file, what you do is you go and grab all the metadata, and then you do recursive build. The metadata that you grab about this jar will help you build this recursive, build the data from the recursive build. And then eventually you're going to get the dependency graph. Same thing you do with the deployable module. You scan for the Debian, and then you scan the content of the Debian. You get all the jars, and then you do the previous step. You do the same thing with the AMI manifest. So you grab the AMI, and you scan the files of all the Debians, and then you do the previous step, which is to scan all the recipients for the content and get the jars. And you can create hashes also in between, so you don't have to repeat those steps. So now we have a system that indexes all the dependency graphs across all the deployable application or deployed applications. So now we can use asterisk to say, given a particular version and artifact ID and group ID, tell me who is actually using this particular library. And then that API call, it's going to get me all the instances or container IDs that is using this particular version of the library. So now we have all the data about which application, which instance, or which container ID is using a particular version of the vulnerable library. Now you end up with so much data. So this is where the second step is required, which is called triage. And so we believe not all the critical vulnerabilities need to be remediated. I think the old school model of remediating every single vuln in the company might not actually work. And this is because of the sheer volume of these vulnerabilities in open source. And also, not all the high vulnerability or high risk vulnerability pose a risk to the organization. It varies. So for the aforementioned reasons, we need to come up with a formula that would allow us to scale the actual triage process. This way, we can understand the true risk that vulnerability poses to Netflix. So this is list of things that we come up with. Relying on CVS score is still a core thing. It's an important thing. But also, we can drive other data. So we can look at the application risk. And application risk is, imagine that you have a particular application that is managing payment information, or an application that is managing PII data. That is considered high-risk application compared to other applications. You can also look at the vulnerable method as executed, and I'm going to talk about that later. And also, you want to see if there is an active exploit in the wild. And this is where, if you have to do that work yourself, then you have to kind of hook into different places to be able to drive this data and be able to tell, like, if a particular version of a library is exploitable. Struts, for example, is a good example of a vulnerability that has an exploit in the wild. And also, you want to see if the app is internet-facing. And also, that's another good signal that will help you. So let's take an example of how that strategy or the risk strategy table looks like. So you have an app that is internet. This is a very trivial example. You have an app that is internet-facing, and there's an active exploit in the wild for that particular version. And the vulnerable method is actually executed. And the application risk is high, and the CVSS is 10. That is really serious problem that we need to take care of it as soon as possible. And so we issue things like PR, campaigns, and Slack messages. I'm going to talk about that also later. This is another example where we think it's insignificant risk for us because there is no active exploit in the wild, and also the vulnerable method is never executed in the application. And also the application risk is medium. This is another example where we think it's moderate risk. So now instead of having so many vulnerabilities or so many list of vulnerabilities and applications that we need to take care of, now we have a very triaged, slimmed down list of things that we can look at. Let's talk about remediation. So in order for you to do effective remediation, you need to have a couple of things. You need to find the minimum version update that will remediate the vulnerability, and this is to avoid updating to a major version that might actually break your application or your build. You want to find the first order dependencies of a vulnerable package. And also you want to identify transitive dependency blockers. So we're going to talk about these now. So imagine you have an application, and that application is using a particular library called foo. So foo is impacted by two CVEs. One is affecting 2.x before 2.4.0, and the other one affecting 2.x before 2.4.9. Now the conclusion here is for the first one to update to 2.4.0, and for the second one the conclusion is to update to 2.4.9. But the actual conclusion for this specific update is we want to ask them to upgrade to 2.4.9 so it can actually fix CVE1 and CVE2. So how do you do that? Snyk has built a really interesting library called Unified Range, and the way it works is, so first you need to find all the ranges from center repository. So given an artifact ID or package name and package org, you can actually pull all the versions from a center repository. And then what do you do next? You go and identify all the vulnerable versions. So in this case, less than 2.4.0 and less than 2.4.9. And you do an exclude process where you actually exclude all the vulnerable versions. Now you have the actual good versions of the library. So this good version will actually give you two things: the minimum version to update to, in case you are worried that you might break something, and also will give you the latest version that updates this specific vulnerability. The second thing you need to find is what we call first order dependency. And the problem is, imagine you're running an application that is relying on a library called A, and that library A relies on C and B, and this is like a nested dependency problem. So in this case, the packages F and H are actually vulnerable. So how do you actually fix this problem? So first, you need to find a way to tell if actually B or E are blockers for this particular problem. So in this case, it's obvious that B and E are blockers for H and F to update. And for an application to update this package, they need to update A to a specific version that will take care of the update for H and F. So the way we do that is, first step is we preserve the metadata from the Git repository in which the artifact was built. So we get this data and we store it. This way we can have all the ownership information about a particular package mapped to the actual package name. The next step is we scan everything published, including all the modules and deployments, and we look for subgraphs that contains the actual thing that is vulnerable. And in this particular case, the actual thing that is vulnerable is the circles in red. So we look at all these subgraphs to see who is actually the immediate consumer of that thing, which is the blue circles. And then, for each immediate consumer, we look to see if the actual library origin, Git repository, matches the actual library. If so, that means it's the same owner, which means they can actually take action on it. So, and then we can do what we could do. We can check, is the consumer using the latest version? Or is the latest version still consuming the vulnerable library? If yes, then this is a blocker. And we never tell anyone else unless that blocker clears. And we keep checking every day to see if that blocker clears. And if it does, that means A has actually upgraded to the version that removes the vulnerability. In this case, we inform everyone else. This is an actual real graph from a campaign that we ran that contains both blockers and services or impacted services. So the pink dots here are actually primary blockers, which means once those primary blockers clears, then all the affected services in green will be able to update. So what do we have so far? We have the list of all the impacted services based on a particular vulnerability. We have a full triaged list of all the impacted services based on the criticality. And we also have the list of all the actionable data about the remediation data about how to remediate specific vulnerability, which includes versions and non-blockers. So when do we actually issue remediation requests? So there are things that requires immediate resolution based on what we have seen in the triage process. So considering a specific CVE. And there are specific things that can actually wait. So for the things that requires immediate resolution, we have multiple options we can use. The first one is what we call resolution strategy and substitution rules. So in Gradle, if you're either using Gradle or Maven, it's the same concept applies the same. You can use the resolution rule plugin, which allows you to actually substitute modules. So you can say, substitute this specific module, which is version 2.0, with this module, which is 2.1. You can do the same with Yarn using selective dependency resolution, where you can actually define the custom package versions inside your dependency through a resolutions field in your package.json. You can also do the same with npm. You can define your resolutions, and then you can enforce it. So it can actually pull the specific version you're looking for. Now, all these resolution rules are great, but it may actually break builds. So how do we actually fix this problem? So there's a solution on Netflix that will build every single repository in the company. So it'll go and fetch all the repositories and build them. And what it does, it gives you some signals about a particular change if it causes any breakage. So it gives you that test coverage to say 90% of the application given this change has built successfully, 10% have failed. So now we know actually which applications that will fail if we issued that resolution strategy or global resolution rule update. The other thing we can do for vulnerability remediation is auto pull requests. And auto pull requests, well, the good thing about it is you can include a lot of context on why you're issuing a particular pull request. So you can include things like the description, references, and all the details that will let developers know why you're actually issuing that particular PR. There is also another system at Netflix that performs dependency lock updates. And dependency locks updates are really a great thing because engineers at Netflix can opt in to receive dependency lock updates depending on their release cycle. So if they have a release cycle every week, then they can opt in to receive their dependency updates every week, which means we can actually hook into this and provide dependency updates for solving specific security problems. The other thing also we can do is what we call security change campaigns. And the concept of campaigns were introduced by Netflix to help decrease time and effort needed to propagate change across all Netflix ecosystem. Also, consequently, mitigate the technical debt. Typically, the way it works is that developers will receive notification in a variety of channels informing them about a particular change that is required and ask them to comply quickly. The crucial part about change or change campaign is that it's actionable, which means, as we've seen the slide before where I was talking about finding actionable applications or packages that they can take action on it. So we can customize the campaigns to only show up on the dashboard of the developers who actually can take action on their libraries. So we issue those, and it will give us really leverage to remediate as many of the downstream dependencies as possible. So in this particular case, we, instead of issuing the campaign to the application, we issue that to the library owner, who's a blocker for other applications to update. This is a example of a campaign we created that causes some security vulnerabilities, and based on our triaging process, we realized that this actually needs to be quickly remediated, so we blacklist any builds that will go into production. And as you can see, this y-axis shows the number of impacted services, and the x-axis shows the time over time, also the decline over time. Now, there are issues that we can wait on, and there are issues that we can act on immediately. So the issues that we can wait on are things that, as I said, insignificant risk that we can actually wait. So how do we actually tackle those type of applications? So another concept we have is to remediate those issues is what we call security deprecation cycles. And the goal of deprecation cycle is to have all the microservices at Netflix rebuilt and redeployed with the latest version artifact every 90 days. So every 90 days, we issue a specific campaign asking the engineers or the DevOps to update their dependencies. We found actually this is to be a very useful thing because first, it's no surprise for developers, meaning developers are actually expecting to see this every 3 months. And also, it's a useful forcing function to purge all the old vulnerable libraries from our ecosystem. This is an example of a deprecation campaign that we created for one of the open source vulnerabilities. And as you can see, the track of deprecation dependency over a period of time, in this example, 5 months. And we can see plateau here after month of June. So what work is still needed for us to finish this project? Well, we're still working on figuring out the vulnerable method use detection, and we also need better remediation, and we want to provide some organizational metrics. So the idea behind vulnerable method use detection is given a particular application or code, can we tell actually, given that you know the vulnerable method upfront, if that vulnerable method is ever executed? So that will give us actually a really strong signal if we needed to take an immediate action on a specific application to remediate. So you can do this for a variety of languages. And in Java, for example, you can use forward tracing, which you can implement some rewriting for specific functions that will allow you to perform specific actions. So you can say trace from now until like 1 hour from now, a specific vulnerable method and see if it's actually being detected. You can also use hotspot servability agent, which you can also count the method invocation. The problem with this is you need to do this on a live instance, which may actually slow down if you don't have many instances or affects the performance. So the way you could do this is you can take one instance out of rotation, do this, and then bring it back in rotation. And in JavaScript, you can use dynamic instrumentation. In Python, we use monkey patching and Python decorator library. And we're still actually investigating those as well. We want to have better remediation strategy. And given that we have all the information about what to update, what version that we need to issue to engineers to update to, we can actually issue pull requests and issue at the same time Slack bot message that says, hey, to developers, you have this vulnerability, and we have sent you a pull request, and based on our tests, it seems like everything passed. So would you like to merge this pull request? And so developers can go and say like, okay, I want to merge this pull request, or I can wait until my release cycle. Also, we want to have some questions for organizational metrics. And we want to be able to tell how often do we actually see open source vulnerabilities in our ecosystem. We want to also tell how long does it take to fix a particular vulnerability in our ecosystem, and what parts of the organization we can remediate quickly, and what parts will take longer. I think final thoughts here, I would say ignoring third-party libraries risk in your code is like seeing a cavity and you're just ignoring it. You want to empower your developers to use third-party libraries, but make a concrete decisions based on the risk of the OSS libraries. Building automation for open source vulnerability will reduce both risk and operational cost. Auto-remediation for open source vulnerabilities and dependencies is actually hard, but it's also doable. And finally, I just want to take a moment to thank all these folks who actually worked on this project, and without them, this work wouldn't happen. One last thing before I end. What I want you to remember today, when you get back to your desks, is that there is actually a real risk for open source security. And the good news is you can automate most of it. And if you do, you'll save so much time and energy. Thank you very much. So we have 4 minutes for questions. Please use the mics if you have any questions.
Hi. Question? You mentioned that you used some third-party tool to get data on open source vulnerabilities. Can you disclose what vendor or what tool you used to get the data?
So we can talk about that in the wrap-up room if you want. I can share who we're using and what are the additional requirements you need to have for you to be able to automate the solution.
And another question, which is there are some tools, commercial tools available that do some of the things that your tool did. So what made the build versus buy decision in this case?
Yeah, it's a good question. So when we thought about basically building the solution versus buying a solution, we realized that there are a lot of contexts that Netflix has, and we have a lot of internal tooling that we can utilize, that we are able to better perform discovery and remediation. Some of the tools in the market, some of the vendors provide actually really good solutions, but they require some integrations. And also there are some, things that you probably have to build yourself. For example, the ability to find blockers for specific libraries. And those blockers will, I think solutions in the market will not be able to tell you which library, internal library that is pulling the actual dependency might need to go first. You have to define that yourself using policies.
Thank you.
One question, is there any of your work you open source, like tooling?
I'm sorry, can you say that again?
Is any of your work described here? You are open source?
Oh yeah, so that's a good question. So we're planning on open sourcing some libraries that, based on the things that I was talking about, for example, finding the minimum version to upgrade to, being able to tell who's actually, discovery basically of the vulnerabilities, and some things were issuing the actual pull requests and figuring out what Slack bot you need to use. So we're gonna eventually open source a lot of that stuff, but the overall solution we won't be able to, because there are a lot of custom code and libraries built in Netflix that are not open source yet.
Where should I watch for those open source?
Yeah, so if we eventually gonna do that, we're gonna put it on GitHub, Netflix repository. So there is on GitHub, if you search GitHub Netflix/Netflix, then we post all our open source stuff there.
Thank you.
One question about 0 days or things like that. When you have a vulnerability that is published and there is no the solution already available in the open source library, you have a process to snooze and revisit the vulnerability later.
Yeah, so you're talking about, the question is whether we remediate things that are recently found and there's no patch for it, or?
Yes, not yet.
Right, so that's an industry problem, and we don't think we have a solution for it. Although we think that if we know about specific vulnerability, then we can either apply patch to remediate the issue, or we can work with the library owners to be able to patch that quickly.
Thank you.
Thank you very much.